the icon and system preferences and tell it. It seems like it is detecting though, right? Display. Where does it say detect? Not go back. Or actually, it seems that this one
There's no signal on the
Well, it's a pleasure to have Andrea Montanari visit us and give the Google Machine Learning Distinguished Lecture. Andrea, as everybody probably knows, is a professor in electrical engineering and statistics at Stanford University. He's made a lot of contributions to a variety of fields, really, going from coding theory, statistical physics, even high-dimensional statistics, optimization, and so on. Yeah, there are many, many more. He's received, again, many awards, including an SF Career Award, a Prava Research Foundation grant, also the theoretical bronze medal for the theoretical physics by CNRS, and a couple of, or actually many more than I know, I think the Best Paper Prize award. So without further delay, I can hand it over to you.
Okay. Thanks, Arti. Thanks, everybody. It was nice to visit CMU today. I'll be talking about joint work with Adelja Ahmad, who was a student in Stanford and now is at USC. Subha Bratau is a student in the stats department in Stanford. Federico is a physicist in Rome. Okay. So the talk will be about using semi-definite programming for solving really some simple graph estimation problems. Most of what I'll say generalizes pretty much to symmetric matrices, but I think the graph of, the language of graphs is more convenient. And actually the talk will be all about this extremely simple model. So let's call it the hidden partition model. I generate a random graph in this way. There is n vertices. I partition them into two subsets of size n over 2. And then I lay down edges that are conditionally independent given the partition. If two vertices are on the same side of the partition, I connect them with probability p. If they are on different sides of the partition, I connect them with probability q, where q is strictly less than p. So this is an example of an adjacency matrix of a graph. It's a small graph generated according to this model. So if you order vertices in such a way that partitions are contiguous, you'll see a block of, a dense subblock here, two dense principal submatrices, and two sparse one. The problem is, given a realization of such graph, estimate the partition, okay? Or even estimate whether such a partition exists. Does the problem make sense? Yeah? So everybody can here recognize the partition, right? Of course, in reality, edges are not colored. This is the way the matrix is given to you. Can everybody see the partition now? And in reality, they are not ordered. Right? So this is how the graph is given to you. Can anybody estimate the partition now? This is like one of these pictures when you stare long enough and you drink a little, a couple of beers, you'll see an elephant coming out. Right? Okay. And what we try to shoot for is really, in this case, exact phase transition results. Right? This is trying to determine conditions under which you can detect or estimate such a partition. So this is the outline. I'll give some background on the problem and earlier work. Then I'll discuss one result about near optimality of semi-definite programming for this problem. Then take a detour and try to talk about how does SDP work in practice. And finally, hopefully, I'll be able to discuss a little bit of proofs of this problem. And it's based on these 3 papers. Okay, background. Okay, one convenient way to think about this problem is to encode, of course, the partition as a binary vector, and I'll take here a ±1 vector. So +1 if you are on one side. The metaphor is often is that one side is Republican, the other is Democrat. So +1 if you are on one side of the political spectrum, -1 on the other. And the partition is balanced. That means that the scalar product of x0 with all one vector is 0. Say that n is even. And the model for the edge is the following: P if x0i is equal to x0j and q otherwise. Okay? Okay, and actually in all of the talk I'll be scaling P and Q in this way. I'll take P to be a constant over n, A over n, and Q equal B over n. And there is not really a good reason for that other than this is the most difficult case, and we want all to show each other that we are smarter. There is a story that you can say about this, is that if this is a model for social networks, then it's reasonable, with this scaling, the average degree of all vertices is of order 1, right? Actually, the average degree of all vertices is A plus B over n. So, if this is a model for a social network, you imagine that the number of friends that you have is of order 1, that is independent of the number of people that lives in your city. Doesn't scale like, I don't know, the square root of the number of people that you have in your city. Okay. And the specific question I want to answer is the following. For me, an estimator is something that estimates x0. So it's a function xset that takes a graph G. So calligraphic G will be the space of graph over n vertices, and output a vector with entries in ±1. So I want to take a graph and output labels for the vertices. And how do I quantify the value of such an estimator? Where I compute this quantity that are called the overlap. This is the following. I take the scalar product of x hat times x0. And then I take the absolute value and then take expectation normalized by n. Okay? So let's check that this makes sense. If I use the perfect estimator that returns x0, this is n, and so this is 1. So the overlap, the maximum overlap is 1. If I return a random estimator that just tosses coin, this will be of order square root of n, just by central limit theorem. So this will be of order 1 over square root of n. The reason for this absolute value is simply that in this model, as you can see, you cannot determine if you are a +1 or if you are a -1. Everything is symmetric. You can interchange the labels, and therefore you can estimate x0 only up to a global flip. So this is a metric, the overlap, that is between 0 and 1, and we want it to be as close to 1 as possible. And the question that I'm interested in here is something very modest, is can I get the overlap to be strictly positive as n goes to infinity? If this happens, you can also solve the easier problem of hypothesis testing, that is detecting that such a partition exists. All right, does this make sense for everybody? Okay. Okay, so the first question is, can you do it at all? Right? Is there any method that does it, forgetting about efficient algorithms or forgetting about semi-definite programming, etc.? This question was answered in a tight way by Helkanen, Mossel, Joe Newman, and Alan Slide a few years ago, and they proved this very nice result. They proved that there exists an estimator that is better than random, and by this I mean that the overlap is bounded away from 0 in the sense that I described before, if and only if the following magic ratio is bigger than 1, a minus b over square root of 2a plus b. And this actually proved an earlier conjecture by statistical physicists. So let me a little bit pause to discuss where does this number come from and why it makes sense. What is a? Well, a over 2 is the number of friends that I have on my side of the partition. If I am a Republican, this is the number of Republican friends that I have, on average. B is the number of Democrat friends that I have. So A minus B is somehow the signal strength, is how strong is the signal about me. What is A plus B? Well, A plus B is the average degree. Actually, the average degree, let me write it down. I'll come back to this, but it's a useful notation. The average degree is A plus B over 2. Degrees in this model are Poisson. This is an Erdős graph, so the degrees are Poisson. So the standard deviation of the degree is square root of A plus B, roughly. So this is really the standard deviation of the degree. So here you are taking the ratio of the signal times the standard deviation of the noise. So this really plays the role of a signal-to-noise ratio. And this theorem tells something very elegant. When this special signal-to-noise ratio is bigger than 1, puff, you can estimate better than random. All right. Okay, once you answer this question, you want to ask, okay, is there an efficient way of achieving this threshold? Is there any efficient implementation? The proof in this paper is based on some sort of exhaustive search. Okay, and this is actually a question that has been studied, since actually the late 80s in theoretical computer science, dating back to Friese and Karp and others, and they gradually improved kind of bounds, conditions under which estimators work well. So initially, for instance, they proved that if P and Q that are the edge density are separated, then you can do it, and then they went down to smaller values, and Amin Koja-Oglan had basically the result right up to constants. And the question was settled again independently by Laurent Massulier and Moss and Niemann-Lai, and they proved that the same condition is sufficient for an algorithmic, for a polynomial time algorithm. So if you look at this paper, I will not go into details of what these people do, but if you look at what they do, they basically realize that basic spectral methods do not work, basic spectral clustering do not work in this regime, and this is something that I'll come back to in a few minutes. But they look at some, they know very well what are, they understand very well what are the statistical properties, the probabilistic properties of these graphs, and kind of construct smart matrices that are tailored to the probabilistic properties of these graphs. Okay? So these are smart people that understand random graphs and leveraged on this. So this raises the question, what if I'm not ingenious? So first of all, this is not an academic question. I'm not that ingenious. And second, you don't want your model to be, your algorithm to be fine-tuned to the properties of your graph. You want, ideally, your algorithm to be robust. Well, if you're not particularly smart, the first thing that you always do is maximum likelihood, right? So what is maximum likelihood? Well, it's convenient to introduce the adjacency matrix from formatting without. This is the 0-1 matrix that is 1 between entry ij is 1 if and only if ij form an edge, and 0 otherwise. All right, so this is an n by n symmetric 0-1 matrix. And again, we encode our partition with a vectors that is plus minus 1. And maximum likelihood is really the following, is maximizing the sum over ij of aij sigma I sigma j. No? So let's pause a moment. This is kind of trivial, but let's pause a moment. This is doing what? If I and j are on the same side of the conjecture partition, it takes up a minus 1. If they are different sides, they takes up a minus 1. So this is minimizing the number of edges that cross the partition. Yeah? And I maximize this subject to the sum of sigma equals 0, so the partition has to be balanced. So I'm really finding a minimum bisection of this graph. Okay? So maximum likelihood in this case is very simple. It's just minimum bisection of the graph. Okay, just for simplicity, in fact, it's a bit easier to work with the centered adjacency matrix. What I mean by this, well, the probability that any edge is present in my graph is d over n. It's a over n if you are on one side, b over n on the other side, or on average is d over n. Okay? So I subtract from the adjacency matrix its expectation. So this means I subtract from every entry d over n. In other words, I subtract from the matrix d over n times 1, 1 transpose. So this is the centered adjacency matrix. So what I'll do is basically instead that, for simplicity, instead of, I don't like this. Frankly, I'm a little bit annoyed by this constraint. It's not a big deal, but I want to throw it out. And so what I'll do is that I'll maximize A times sigma, sigma transpose. Okay, this is the same as sigma A sigma. I'll just written in a slightly different form, over vector plus minus 1. And I just forget about the balance constraint. You can think of it this as just a Lagrangian version of the previous problem. Because this is the same as sigma A sigma minus d over n sum over I sigma I squared. So before I was forcing sum of I sigma equals 0, I'm just adding it as a soft constraint. So think of this as a regularization parameter or a Lagrangian. Okay? I just like it better. Okay, of course, this is MPR, right? I didn't discover anything. This is hard to approximate. Problem. So semi-definite programming is a very natural and non-convex relaxation for this problem that does the following. Okay. What I'll do instead of maximizing this, so this is now, when I write it for matrices, is the product between matrices. So AX is really trace of A times X. Okay. So what I'm doing here is, instead of maximizing here over the matrices that can be written as sigma, sigma transpose, I'll maximize it over all matrices X. There are positive semi-definite, they must be symmetric. Positive semi-definite have diagonal entries equal to 1. If I add the additional constraint that the rank of X is equal to 1, I will get again the original problem, because any matrix like this with the rank of X equal to 1 can be written as sigma, sigma transpose. But I throw out that constraint. And now this is a convex program. Is everybody okay with this? Okay, so we went to a few slides, but this should be completely boring to you. This is completely off-the-shelf algorithm. It's something that any master student in engineering learns how to do. And the real question is, how well does it work? Okay, this is the result that we have. Okay, first of all, I want to take a little detour because it's useful and discuss a little bit what is the problem with standard principal component analysis for this problem. Okay, so why should you use principal component analysis or spectral clustering? Well, if you think of your matrix A, or the centered matrix A, I rescale it by square root of D. You do a little calculation, and you see that in expectation, this is x naught transpose times a constant. Because, you see, on one side of the partition, I get A over n minus D over n times some scaling. If they are on different sides, you get B over n minus D over n. This is one opposite of the other, so you get x naught transpose. Now the constant turns out to be this magic ratio, which I'll also copy here so that you remember it. So lambda is A minus B over squared. So nicely the magic ratio pops out. Now the difference with respect to its expectation is a matrix of zero expectation. And the reason for this normalization, if you look at the standard, the variance of its entries, it's 1 over n. So this looks like it's a Wigner matrix. So you would say, okay, this is a rank 1 matrix plus a Wigner matrix. The norm of this Wigner matrix is of order 1. The norm of this matrix is lambda. The norm of this matrix, you would think is of order 1. The norm is lambda. So if lambda is a constant, PCA should work. Okay, so if the operator norm of this beats the operator norm of this, it should be in good shape. If you do just principal component analysis, it will recover a vector correlated to x0. Okay, these are parameters. So the naive PCA estimator is the following: center the matrix, compute the principal eigenvector, and take the sign. Does it work? No. Well, this is why we're trying to, we're still working, right? And the reason why, okay, summarized here is the following. If you look at the spectrum of this noise matrix, of this rescaled adjacency matrix, now if you take, this is a small experiment in which I took in one case d equal 15, in the other d equal 1.5. So if the degree is large, the spectrum is very close to the semicircle, and the norm is 2, at the edge of the semicircle. If the graph is sparse, you have these tails. These are called Lifshitz tails, and actually these tails are unbounded. So what's happening here is that there are vertices that have degree much larger than the average degree. In fact, the largest degree in such a graph, the degrees are Poisson. The maximum of n Poisson is above the log n over log n. So there are degrees that are as big as log n over log n. Now, this induces eigenvectors that are completely concentrated on high degree vertices, and the corresponding eigenvalues is square root of log n over log n. You can just take, way to prove it, it's very simple. You just compute A times EI norm. So this is a low and bound on lambda max. This is the proof of this theorem, basically. I mean, it's one side of the theorem. So you take I to be the vertex of largest. Okay, so this is more than a theoretical problem. You see it's also in the eigenvector. If you take a graph of large degree and you plot the leading eigenvector, this is the first side of the first community, the first cluster is the first n over 2 vertices, the other is the other n over 2. You see something, an eigenvector that has clearly some signal, is mostly positive on one side of the partition and mostly negative on the other side of the partition. So you can do, just threshold this and get a positive correlation. Well, if I take small degree, here is degree 3, what happens is that there is this very weird and erratic noise, and this noise you can check that is due to the fact that you have vertices of very high degree. These spikes are vertices of high degree. Okay, so this is why naive spectral clustering fails. So why should SDP work a little bit, work better? Well, SDP has this additional constraint, right? As the constraint that the element of the diagonal have to be equal to 1, so this morally is forbidding eigenvectors that are very localized, or solutions that are very localized on a few vertices. Okay, so remember, this is the information theoretic threshold, says that, with this definition of parameter, you need, you can do it if and only if lambda is bigger than 1. Lambda is the SNR. And this is the theorem that we proved, says that the SDP estimator, now we look at very specific estimator, SDP estimator has a positive overlap, so it's better than random if lambda is bigger than 1 plus something that goes to 0 with the degree. Okay? Well, how it goes to 0 with degree, you can go through our proof and get some polynomial decay. As we'll see in the moment, reality is much better than this, so we don't bother too much to go through bounding these constants. So this doesn't tell you that SDP is optimal for any bounded degree, but is optimal when the degree is bounded by large, or nearly optimal. Any question about this? Okay. Okay, so there is one thing that I didn't explain, and you should have asked the following. I described what is the SDP, the relaxation, but I didn't describe how to come up with a partition of the vertices. What you want really to come is a plus minus. So in CS language, you want to round your SDP. So how should you round it? I'm going to tell you how should you round it, and then you can ask me how your proof works, because the way you should round it really is the following. You take the solution of the SDP, x star, any optimizer. Then you compute the principal eigenvector of x star. And then you take the sign of that principal eigenvector. This, both empirically and heuristically, we have calculations for this. This is the best thing to do. So this is a kind of two-stage procedure in which you first solve the SDP, and then you do principal component on top of the SDP. In reality, for the proof to go through, we use a few more tricks. So we use something that is not like this. In particular, we don't take the top eigenvector, but we take one eigenvector at random. So if you decompose x star is sum over I xi vi transpose. So this is the eigenvector, the eigenvalue decomposition of x star. Now, by the trace constraint, sum over I, the diagonal constraint, this is equal to 1. So I can interpret xi I over n like as a probability distribution. So you pick eigenvector I with probability xi I over n. And then you round that vector. So you sample an index I with probability xi I over n. The advantage of this is that if you take Vi now, Vi transpose times the adjacency matrix, you have some lower bound of this. The expectation of this is E of A times x star, and our analysis gives some lower bound. So we cannot say, having a lower bound on this doesn't imply that the top eigenvector is good necessarily. It implies it if you are, but it's not tight. So if you want to get the right threshold, this is the trick that works. And there are a couple of other tricks. Okay, so the real, as I was mentioning, the real technical result, if you look pre-rounding, is really a result about the value of the SDP, and is the following fact: if you take the graph from this model, called this model ND lambda, then there is this phase transition. If lambda is less than 1, then if you take the SDP, you evaluate the SDP on the problem with the data A, and you normalize in the way you should. So you normalize by 1 over n, because the diagonal of x is the trace of x is n, and you normalize by square root of d, because all of these things, like the norm of this matrix should scale as square root of d, so you should normalize by square root of d. This is 2 plus something that goes to 0 with d. All right? So by comparison, you can look at the largest eigenvalue of this matrix A. So we said before that, so we have 1 over n SDP of A is less or equal than the principal eigenvalue of A. So this is the center matrix. Now we said before that this is of order log n over log n. So this is very bad. But this instead behaves very nicely. It's 2 square root of d. So this is what you would get if the graph was regular, roughly, with degree d. And what I mean is what you would get up to, with the right constant, that is 2. So you get to the edge of the semicircle. Now, if lambda becomes bigger than 1, this value becomes strictly bigger than 2. So bigger than 2 by a quantity that is especially positive. So this is a phase transition result of the SDP value for sparse graphs. Right, so again, to emphasize previous work, in this problem there are a number of papers that gives polynomial time algorithms that achieve the same phase transition. Yeah.
Do you know the eigenvalues of x star to give? Approximately like 1 or?
It's not approximately in the sense that, okay, for instance, if you want to look at, so we tried to, we don't know, we don't have any rigorous result, but we did a lot of simulations about this. And if you look at the first, look at how many eigenvalues you need to sum up in such a way that you get 99% of the total trace. So you want to sum over I1 to k xi I bigger or equal than n times 1 minus delta, say. So this is a k of delta. Now this k of delta turns out to be of order 1, but not 1. So the second eigenvalue is the same order as the first. It's smaller, but of the same order as the first. And they think this k of delta seems to be random, so the eigenvalues, I don't think they... Okay. I don't know. They seem not to concentrate, but... So this is not essentially a rank 1 matrix. It's an order 1 rank matrix. Okay, so there are several papers, presenting, as I mentioned before, spectral algorithms for this problem. And probably the most natural spectral algorithm is the one in this paper by Bordenave, Lelage, and Massoulier. There are several papers analyzing SDPs for this problem, but these are all focused on a different regime in which the average degree is of order log n. So in that regime, the solution of the SDP turns to be of rank 1 with high probability, so not essentially of rank 1, and actually turns out to be the exact with high probability. So the analysis is very different there, because what you have to do is basically, you know what is the optimal point, or the conjecture, and you want to kind of bound the deviation from this point by coming up with a good dual widthness. Here, as you will see, is very different, because we don't know what is the solution of the SDP. It's a random point that is not the ground truth. And finally, in this regime, there is only one paper that looked at this SDP, and this by Olivier Guédon and Roman Vershinin, okay, it's a very different proof and requires this lambda to be a big constant. So it's not 1 plus mod, but it's a big constant. But it's a very interesting paper. Okay, any question about this?
Well, what kind of for replacing? I mean, you didn't relax the constraint to be trace, but to be the diagonal. Does that clear it?
Well, if you put the trace, if you replace my SDP by trace of x equal 1, so you could replace this, relax this to this, then this outputs the leading eigenvector of A. If you solve this, you maximize A times x subject to this. The output is x equal B1 transpose. So this is no better than just doing principal component analysis. So it doesn't work. And the reason it doesn't work morally is that you are not imposing the entries of B1 to have all the same size roughly. So you can get highly heterogeneous stuff. So it's crucial the fact that in the SDP we have this added freedom of imposing all the diagonal to be constant. So if there is one thing that I learned in this whole thing is this difference. Yeah.
So did you forget about you told us earlier that you dropped this constraint that the sigmas have to add up to 0. Mm-hmm. So does that happen in your rounding? Does that come back in your rounding?
Yeah, so what happens, okay, so if you look at the analysis of the model, or if you run simulation on this thing, what you get is in the end is that the solution adds up to something that is not 0, but is of order square root of n versus n. Okay? So you can add an additional, if you want to impose that constraint, strictly, you can flip a small number of vertices and enforce that constraint, and you don't change anything basically in the final result. But in reality, in practice, you don't really. There is no reason why you search for an exactly balanced partition, but you can do that.
So this E equals theta log n regime, still PCA doesn't work, right?
Yeah, still PCA, but okay. So most of this paper basically doesn't work in the sense that it doesn't return the correct thing, but some of this paper are based on you do some modified version of PCA and then you do a local improvement. For instance, there is a paper by Van Wu, so I don't remember whether it gets the right constant, but it basically does that. It does principal component, it throws out vertices with I degree. This is a trick due to Feige, Ofek, and same trick used by Kojaglan. So it throws out vertices of I degree, does the principal component analysis, and then does some local improvement over that. So re-estimate every vertex exactly, and then that gets some bound on that, right? Other papers do one step of SDP and then they do some improvement. Other papers do just plain SDP. On that regime, there are several options. Okay, just one piece of notation. I call lambda C the threshold for optimal tests. Information theoretically optimal, and this is the threshold for the SDP-based test or SDP-based estimator. And you know, this we know that is 1, this we know that is 1 plus more law of 1, so this begs the question is, how big is this more law of 1, right? After all, you're interested perhaps in d equal 5 or 10, is this a billion or 3 or something? So what we did is, okay, we did, first of all, a lot of simulations, and second, we did some non-rigorous statistical physics calculation. So my background is that I'm a physicist, and so if there is one thing that you learn as a physicist, that there is nothing you cannot compute. Most of things you cannot prove, but most of things you also can compute. So this is here average degree 5. We simulated 500 samples for this size of graph, 2,000 up to 16,000. And you see what happens here. I'm plotting the overlap versus this magic parameter lambda. And what happens when you are below 1, as the size increases, the overlap tends to get smaller and smaller. Okay? On the other hand, above 1, as the size increases, this seems to converge actually to be pretty much independent on n. And actually, it converges to a limit curve. And actually, we have a computation for this limit curve, that is this black line. And it matches very well the data. Okay? So if you look at this graph, now it seems to be a phase transition here. Here it goes to 0, here it doesn't go to 0. This is perhaps not 1, but it's very hard to distinguish from 1. So the phase transition point of SDP is very close to 1 for d equal 5. Now you can repeat this for other d's, and you get that again is very close to 1. It's impressively close to 1, actually. Okay, so now, okay, you can try to estimate this phase transition from points from data, just to see where it is. How we did it is a long story that you know, it's interesting if you're interested in data analysis, and I can talk about it. But this is what we get, the final result. This is versus D, and the point are the numerical results. So you see, for basically any degree, it seems to be that the phase transition of SDP is not 1, but is at most 2% away from 1. So in a sense, SDP is not optimal, which is interesting, but is at most 2% suboptimal, which is also interesting. And this is again a calculation for it. There is a paper by Ankur, Moetra, and Perrin that suggests that actually this should be strictly small, bigger than 1 for this small. So it's not really a proof, but it's a strong argument direction. It shows that if you assume some robustness properties, then it should be bounded away from 1. Okay, so so doing this simulation took us 10 years of CPU time. But still, I think it's pretty short time. So if any of you try to solve an SDP, it should interrupt me and be kind of impressed, because here we're solving SDP of size 16,000. So this means finding a matrix with 10 to the 8 entries, right? If you put this in CDX, don't laugh, or in MATLAB, whatever, it screams at you after 200, right? So you should ask me, you're saying you're kidding us, this is BS, or something. How did you do it, right? Okay, so we can do it after to 10 to the 5 in a matter of minutes. We have code here, and we use the dirty trick. So I'll call it the Burero-Montero trick, because since it's a dirty trick, I have to do somebody else. No, it's a beautiful trick, I think. The more I think about it. And the trick is the following. So you want to solve, I have it inside actually. You want to solve this SDP. What I actually do, I throw in the rank constraint. All right? So I impose that the rank to be less than k, and actually k equal 20 just works like a charm. All right? So you might, okay, why this is interesting, first of all, because once you do this, then something nice happens is that you can solve this SDP constraint. You can write just xij as the scalar product of two vectors, sigma I, sigma j. Any PSD matrix of rank k can be written as a gram matrix of vectors of length k, and the trace constraint tells me that this vector have to be norm 1. Now this is a smooth problem that we are solving over a smooth manifold. It's a product of n spheres. And the way that we solve it is completely stupid. We just take in turn, we take each vertex I, and we optimize with respect to sigma I. It's very easy to optimize this function with respect to sigma I, because this is optimizing a linear function of the vector sigma I over the sphere. So nothing is, it's just you are maximizing. At each step, we are maximizing something vi times sigma I over the sphere. So, and vi is sum over j mij sigma j. So the solution is sigma I equal vi over vi. This is one case in which I can write the code for this algorithm on the board into that. And this works very quickly. Okay, so this is a dirty trick because, you start with a non-convex problem, you convexify it, you prove something nice, and then you deconvexify. What are you talking about, right? So one thing is that you can check in a number of ways that the value that you obtain are very good. For instance, you can extend the rank. There are conditions under which this is diet. You can compute the duality gap. You can start from different initialization. So you can be very confident that this works well. And what is the picture here? So I'll draw a kind of intuitive picture here. The picture here that I think is very interesting is the following. We start with a problem that is highly non-convex and orderable, or is on plus minus 1. Then we convexify and we get something beautifully convex. And now this is k equal 1. This is k equal n. And now don't jump suddenly from this to this when n passes, k passes n minus 1. They kind of very quickly transition from this to this. So if you get k equal 20, the function is like this. So even if you do something local, even if it is non-convex, you are reaching something very close to the optimum.
Is that intuition? Do you think that intuition will hold if X is not really a perfect idealized block model?
Okay, yeah, okay. So question is, does this intuition depend on the statistical model that you're assuming on the data or not? Yeah? So I think it's very interesting to try to prove things about this picture. All right, so I thought a little bit about it. And this is one thing that I can prove. It's actually one thing that it's 2 pages, but it's so surprising that I'm still uncertain whether it is correct. So please check the proof. But it's the following. It says the following. Take this function that I'm trying to optimize. I call it fm for any metric m. Okay, now I'm looking at it as an optimization problem, so a maximization problem. So let me redraw this picture just to be clear. So you have this convex, and then here the optimum of the convex is SDP of m. And now I have this non-convex function for some finite k, say k equal 20. And this is some local maxima. So this is take any local maximum, and take the difference between this and that. Okay. So the difference between this and that is basically of order 1 over square root of k, the relative difference. So this is relative difference in the following sense. The error really depends on the operator norm of M, but typically in cases that we are interested in, the operator norm is of order 1, and the value of the SDP is of order N. Okay, so what this means is that if you want a relative difference between some epsilon, it's sufficient to take k that is of order 1. Which is kind of surprising, but it's what we see in practice. There was earlier result that says that this non-convex problem has no local maximum by Buran and Montero themselves, but requires k to be bigger than square root of 2n. So this is not what we see in practice. In practice, we take n 100,000, and k we take it to be 10 or even 5 or just. So I call this a Grothendieck type inequality because it's similar to Grothendieck inequality. Grothendieck inequality gives some bound on the difference between the global optimum of the non-convex problem and the global optimum of the convex problem, while this is, in a way, okay, for what we are interested here, it's more interesting because it's about local optima on the non-convex problem. Now, just to emphasize, this doesn't tell you that we can achieve the local optimal of the non-convex problem. This is a problem in itself, but give confidence that these methods are useful. Any question? All right, so there is related work, also a few weeks back by Afonso Bandera, Nicola Bulamal, and Vlad Voroninski. They looked at the same question, so how comes that these non-convex formulations actually work? But they look at this specific Z2 synchronization problem, but they take and they assume that the SNR is strong enough. But in this case, they take k, an extreme, the first non-convex thing that makes sense, that is k equal to rank 2. And they still show that it works. Now, in a sense, I like this better because here I'm not assuming that there is a strong signal. Okay, one last thing that I want to talk about, how to do this in practice is this approach robust to model misspecification. After all, the model is not necessarily correct. So this is a small simulation that we did in which we take the stochastic block model and then we do the following. We take a fraction alpha of the vertices and we connect all of their neighbors. This is something that makes sense if you think about the social network story because friends, my friends are more likely to be friends between each other than any two random persons. So real networks have much more many more triangles than these random graph models. So you take alpha vertices and connect their neighbors. This is alpha is small. So this is the black line is the original model, and this is the overlap versus lambda. And so what we simulated here is this SDP performance, and the performance of one of the spectral methods. Basically, it's equivalent to this non-vectoring work, and they both work beautifully, right? So they both have follow this curve and have the phase transition at 1, etc. Now I crank up a little bit of alpha. For instance, I put 2% of nodes that are these outliers nodes. And what happens to the SDP is not much, right? It goes from this continuous black curve to this red continuous curve. So it deteriorates a bit, but not much. But if you look at the spectral method, pops. It jumps down. And of course, if you increase it. So the spectral method is fragile. This is not completely surprising. I constructed the perturbation because I understood how the spectral method works and I wanted to break it. Okay, so in the last 5 minutes, perhaps, or 10 minutes, I want to talk a bit about proof ideas. So as I mentioned, the main technical theorem is this one, that the SDP value is 2 if you normalize it below the phase transition, and 2 plus something strictly positive above the phase transition. How do we prove this? So the proof goes basically in 2 steps. First, we prove that this model for large degree is equivalent to a certain Gaussian model, and then that is interesting per se, and then we analyze the Gaussian model. Okay, so I'll do first the step 2 because okay, I don't know why. So this is the Gaussian model. It's very simple yet interesting problem. Is what people call Z2 synchronization is the following. You have a signal x0 that is a ±1 vector, and you have a constant times x0 transpose plus w, where w is the GOE matrix. So it's a symmetric matrix with entries above the diagonal independent and Gaussian with variance 1 over n. All right. And you want to reconstruct x0, and here things are scaled in such a way that the operator norm of this is of the same order as the operator norm of that. A lot is known about spectral properties of this graph. There are these metrics, there are hundreds of papers about it, but here we need to do something very different, just analyzing its SDP properties. So let me just, for presenting things, define S of lambda will be the limit of the SDP value when R is scaled by 1 over n. Now I don't know that this limit exists, so I have to define S overline and S underline that are the lim sup and limit. I don't know it in general. But. And again, SDP is the maximization of B times X over the electrode. So the analysis of the Gaussian model is encoded in this theorem, says that if the signal is less than 1, then the value of the SDP rescale is exactly 2 in the limit. If lambda is bigger than 1, then it's strictly bigger than 2, and okay, you can get the probability bound. Okay, so how do we go about analyzing this? Well, let's start from some simple fact. First simple fact is that the value of the SDP is upper bounded by the largest eigenvalue of this matrix, of course. And largest eigenvalue of this matrix, some people have computed it for us. It's 2 if lambda is below 1, and this bigger than 2 is lambda plus 1 over lambda if lambda is above 1. So this is the phase transition. The eigenvalue is known also as the Weich-Benarus special phase transition. Other trivial thing that we know is that we can plug in any matrix X, any witness X, and get a lower bound. So in particular, if I put the ground truth, I get B times 1 transpose that in the limit is lambda. Other trivial things, these two functions are non-random by concentration of measure, and they are non-decreasing by so this is what we get from these arguments. We get this upper bound, this is the eigenvalue, and this is lower bound. Now what we need to show that this is 2 up to here, and then goes above 2 above that, right? So we have a long way to go still. So we go in 2 parts. First part, we prove that at lambda equals 0, this is bigger than or equal to 2. By monotonicity, this implies that it's bigger or equal than 2 everywhere. Okay? Now, this implies that the SDP must have a phase transition, but now this phase transition can be anywhere between lambda equal 1 and lambda equal 2. It says that the SDP value is here, but can detach from the purple line any point. So there is a second part in which we take lambda 1 plus epsilon, and we prove that S is strictly bigger than this. Therefore, we get some other lower bound like this. And all of these 2 lower bounds are really proved by what you would think is the most straightforward path, but is a little bit of a pain to implement it. That is, you construct a feasible point X and you lower bound the value of this feasible point. So the first part took me perhaps 1 week to do it. All the things that is to come up with the right X right here in this tree. First thing taking me perhaps 1 week. The second took me 3 months. I was not thinking to it all the time, but before I had the right idea, because you can do slightly different things and then it doesn't work. One day I woke up. So the first part, lambda equals 0, is simple. So this is the spectrum of this matrix. So the naive thinking would be, okay, you take the principal eigenvector of this matrix, and then you take V1 transpose. Problem is that if you take this, the entries on the diagonal are a square of a Gaussian random variable, so they are not 1 at all. So what you do? Well, the idea is the following. I take n times delta, say, eigenvectors of this matrix, the leading n times delta eigenvector. So I form a very skinny matrix with this eigenvector. All these eigenvectors have very good value, right? Because there is n times delta eigenvector that have eigenvalue at least 2 minus epsilon. So I lose only epsilon in the value if I go up to delta. But now what is nice about this matrix is that if I compute the norm of each of the rows of this matrix, so I take U transpose and diagonal of that, this is basically the identity. The norm of all the rows of this matrix are basically 1. Why? Well, because each row of this matrix is a projection in n delta dimension of uniformly random unit vector in n dimension. Therefore, it's basically like a t-square random variable with n delta degrees of freedom. So this is, so this is basically okay. You add only these two enforce the constraint of the diagonal, and this just works. Now, what happens above 1? Above 1, there is this BBAP phase transition, so there is one eigenvalue that pops out. Now, you want to kind of earn some of the value that is given by this eigenvalue. So ideally, we would like to put some weight on this eigenvector. Unfortunately, again, this eigenvector is obnoxious, so it's below 1, above 1, it's not constant, right? So what we do the following. We take the eigenvector, we rescale it in some way, in such a way to have all the entries of order 1. We make it really small by multiplying by epsilon, and then we threshold it. Okay? So we take this eigenvector. This eigenvector is something like this. Can be negative, etc. We rescale it. We still have epsilon of its value. This can have some big spike, and we cancel the big spikes to get rid of the big. And then at this point we are not done because this doesn't work. We have to take the idea from the port for. So take some of the eigenvector from second to the n delta, patch them together, and then so construct this diagonal. So take this phi transpose plus U transpose and fix this with some additional bit. Now this works. So now this perhaps addresses a little bit of your question because this is not the optimum, it's just a witness, but it's definitely not a rank 1 witness. And you see that we were forced somehow to take not a rank 1 witness because the only way to do it with a rank 1 will not work. So this is the analysis of the Gaussian model. Then we have to prove equivalence to the Gaussian model. That is, we have to prove the following, that if you evaluate the SDP on this set adjacency matrix, is the same as SDP for the Gaussian matrix. So what we do here, well, we view these two as function of these two matrices. So SDP is a function of a matrix. So you want to prove that two functions of two sets of random variables are basically closed. It's sufficient to do it in expectation because this stuff concentrates. So we use Lindenberg method, which is basically a word to say we replace each of the variable one of the time. So these are Bernoulli. We replace Bernoulli by Gaussian and Bernoulli by Gaussian, and we bound the error at each step. Okay, this is a little bit. So in one case we have Bernoullis. These are Gaussian. So if you look at Lindenberg method, this is has been used by many people in standard in random matrix theory. This is a modification, for instance, of a lemma that is also in Chatterjee's work. But Lindenberg method always tells you the following. If you want to bound the difference of the expectation of two functions under the distribution, what you have to control is the second derivative and the third derivative, the second and third derivative, partial derivative of this function with respect to each of its coordinates. Now the pain here is that my function is the SDP value on that matrix. Now you want this to be C3, right? To have even finite derivative, and this is not C3. It's not C3 because if you look at the elliptope, so this is optimizing a linear function over a convex set, and this convex set in this case has some edges, and so you get singularity. And so we have to smoothen it. How do we smoothen it? We rewrite this in this way, in this non-convex form. Okay, so again, I'm a physicist, and one trick that I know is the following. This trick, that if I want to do max I know that max of A and B is an annoying thing because it's non-differentiable, but it's about the softmax, right? So we replace this max with this kind of partition, log partition function where we integrate over sigma. So it's just a more complicated version of this. Now, once you do this, you seem to be happy because your function is C3, but then you have to bound, of course, you have to bound the error that you make in going from beta equal infinity to beta finite. You try to do it, we try to do it, it doesn't work. Because somehow the difference is related to the entropy of the space that you are integrating over. So what we do is that we, instead of integrating over the n-dimensional sphere, we integrate over a k-dimensional sphere, and we bound the error by the quantity. All right, so this is the 5-minute version of the proof. The main take-home message from a practical point of view for me is that SDP is much better than PCA when data are heterogeneous. I didn't understand this before proving all of this stuff. It's an obvious thing, but I think it's very important. And you know, from a theory point of view, there is a lot of information about spectral properties of random matrices, norm of random matrices, eigenvalues of random matrices, but very little is known about value of the SDP. The SDP values with random matrices, for instance, even value with this spiked model, lambda over n xx transpose plus Gaussian, we know everything about the eigenvalue of this. We don't know. We know only the simple bounds that are proved about the value. We don't know the value. Yeah? That's all.
We can take questions now.
When n is bigger than 1, some positive overlap. What's known about if you want to get that overlap close to 1 by some subsequent maybe local search? If they're positive results?
About a specific method or about any method?
Any method, yeah.
Well, what you mean for the block model or for the thing? So it should be that lambda, if you want to get 1 minus epsilon, is sufficient to prove something like get lambda to be log of 1 over epsilon, or I don't know whether log or square root, perhaps square root of log even.
This is without any post-processing, or you just do the...
with the SDP you mean?
Yeah.
Okay, so with the SDP, I don't think it's known. It's known with other methods. For instance, this paper by Wu, what they do is they do the truncation of the degree, the spectral method, and then some local optimization. Now I don't remember, but they have some bound of this type. I don't remember whether they get it right or not. Now with the SDP, I don't think there is anything about that. But yeah, I don't think there is anything. I mean, okay, no, I'm wrong. The paper by Guedon and Verschinin has a result like that. Right? That works. It's really like this. It works when lambda, provided lambda is bigger than 10 to the 4, then you get something like the error is bounded, I think, in this way.
So I guess that was based on simulation?
No, so I have added the simulations and the curve. So that curve is theoretical. So we have an exact prediction for the theoretical but not rigorous. We have an exact prediction for the Gaussian model. It's basically a closed form expression. It would be very nice.
So like that curve is not quantitatively achieving the log 1 over epsilon?
That curve, it is. So that curve is it's really about this method. That is, you do the SDP, and then you take the principal component of the matrix, and then you take the sign of that. So that is the post-processing. And there is a closed a formula for that curve. It's a complicated formula, but it's a formula. And like that.
Are the results for when there's more than 2 blocks? Did everything carry over?
So we did the analysis for k blocks that are all equal, and basically everything goes Okay, we did the analysis for what concerned the testing problem, testing the null versus the alternative and getting the phase transition, and this gets the kind of spectral phase transition. So what it should be, that is a minus b over square root of a plus k minus 1 times b. So this is group, so this is the testing. We didn't do the rounding, and we didn't do groups with unequal size. It would be interesting to try to do that. Of course, we realize.
So when you formulated the estimator, differently from a linear classifier where the loss was kind of the variance. You wanted to find the projection that maximized the variance of the SDP points. And when I see that, I wonder to myself, like, what if, because the variance is like a squared error, that's going to be dominated by these kind of big vectors produced by the SDP. So do you think there's any room for, let's say you trained a better classifier, a better linear classifier, according to a loss function which was less susceptible to one of these outliers, that you might, is there any room for a better rounding, do you feel? I know that quantitatively things seem pretty good here, but maybe for small d.
So not within this model, I don't think within this model. But you can modify the model and add outliers, so perhaps then it will work. But the point of all of this, or the beauty of all of this, is that putting this constraint on the diagonal in the SDP has this nice thing of basically regularizing thing, right? Because basically what happens is that is insensitive to any small number of edges. So you can add the vertex with very high degree. And this, if the total number of, if the degree of this vertex is smaller than the total number of edges of the graph, this has small impact, right? So, yeah.
So you're saying the norms of all the vectors are
yeah. Yeah, so all the vertices are taken into account equally, right?
Another question? Let's thank Andrea again.
Hey.